Imagine pointing a telescope at a faint star just 190 light years away, running the numbers on its age, and getting a result that should be impossible. Not just old, older than the universe itself. That's exactly what happened with a star called Methuselah. When astronomers calculated its age, the answer came back at roughly 14.5 billion years. But the universe is only 13.8 billion years old. Nothing can be older than everything. Nothing can predate the moment existence began. And yet, there it was, a quiet, dim star drifting through our cosmic neighborhood, casually defying the most fundamental timeline in all of science. Either our understanding of the universe's age was wrong, or our understanding of how stars age was wrong, or something far stranger was going on. Tonight we're going to unravel this paradox from the beginning. If you find these kinds of deep cosmic mysteries fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Now, let's begin. There is a star drifting through our cosmic neighborhood right now that almost broke modern astrophysics. Not because it exploded, not because it collapsed into a black hole, not because it did anything dramatic at all. It broke astrophysics simply by existing and by being far too old. Its catalog name is HD 140,283. Most people have never heard of it. If you walk outside tonight with a pair of decent binoculars and pointed them toward the constellation Libra, you could find it. It's faint, just barely too dim for the naked eye, but visible enough through glass. It looks like nothing special. A quiet point of light lost among thousands of brighter stars. You'd pass right over it. You would have no reason to stop and stare. But this star carries a secret that kept astronomers awake at night for more than a decade. When researchers calculated how old it was, the answer they got was roughly 14.5 billion years. And that number should be impossible. Because the entire universe, everything that exists, every galaxy, every star, every atom of hydrogen and helium and oxygen and carbon, all of it came into being approximately 13.8 billion years ago. That is the age of the cosmos. It is the starting line. Nothing can predate it. Nothing can be older than the event that created time itself. And yet, here was a star whose estimated birthday appeared to fall before the universe even existed. Not by a small amount. Not by some rounding error you could wave away. The gap was roughly 700 million years. That is not a minor discrepancy. 700 million years is longer than the entire history of complex animal life on Earth. It is longer than the span from the first trilobites crawling across ancient seafloors to you sitting here tonight. The star's age didn't just nudge past the boundary. It overshot it by a margin large enough to contain entire eras of biological evolution. Astronomers nicknamed it Methuselah, after the biblical figure said to have lived 969 years, the oldest person in scripture. The name stuck because nothing else captured the absurdity quite as well. This was a star that seemed to have been burning before there was anywhere to burn. Let's talk about what Methuselah actually is, because understanding the star itself is essential to understanding why the paradox emerged. HD 140,283 is what astronomers call a subgiant. That term describes a star at a very specific stage in its life. For most of a star's existence, it sits on what's called the main sequence, steadily fusing hydrogen into helium in its core, radiating energy outward holding itself in balance. Our sun is a main sequence star right now. It has been one for about 4.5 billion years, and will remain one for roughly another 5 billion. Main sequence life is the long, stable middle chapter of a star's biography. A subgiant is a star that has just begun to leave that stable phase. The hydrogen fuel in its core is running out. The core is contracting. The outer layers are starting to expand and cool. It hasn't yet swollen into a full red giant. That bloated, dramatic final stage you see in stars like Betelgeuse. It's in between. It's transitioning. Think of a subgiant as a star entering its retirement years. Still functioning, still burning, but beginning the slow transformation that will eventually end its life. Methuselah sits at roughly 6,000 degrees on its surface, slightly cooler than our sun, and it shines with a luminosity a few times greater than the sun's. It's not a massive star. It's not a tiny one. It's modest in almost every measurable way except one. Its chemistry is extraordinary. When astronomers analyze the light from a star, they can determine what elements that star contains. Every element absorbs light at specific wavelengths, leaving dark lines in the star's spectrum like a chemical fingerprint. By reading those lines, you can figure out exactly what a star is made of and in what proportions. When researchers examined Methuselah's spectrum, they found something striking. The star is almost entirely hydrogen and helium. It contains only a tiny trace of heavier elements. Its iron content is roughly 1/250th that of our sun. In astronomical terms, that iron to hydrogen ratio is astonishingly low. To put this in perspective, our sun is relatively rich in heavy elements. It contains iron, oxygen, carbon, silicon, magnesium, and dozens of other elements forged in previous generations of stars. Methuselah has almost none of that. It's chemically primitive, made from material that existed when the universe was barely getting started and had not yet had time to produce many heavy elements through stellar life cycles. This chemical fingerprint is one of the things that originally drew attention to the star. Astronomers recognized early on that stars with very few heavy elements tend to be ancient. The logic is straightforward. Heavy elements are manufactured inside stars and scattered into space when those stars die. Each generation of stars seeds the cosmos with a slightly richer cocktail of elements. The very first stars in the universe form from nothing but hydrogen and helium, the only elements created in the Big Bang itself. When those first stars exploded, they enriched their surroundings with small amounts of heavier material. The next generation of stars formed from that slightly enriched gas. Then those stars lived and died, enriching the gas further, and so on, generation after generation, each wave adding more complexity to the cosmic recipe. Our sun, born about 4.5 billion years ago, formed from gas that had been recycled through many previous stellar generations. That's why it's rich in heavy elements. Methuselah, by contrast, formed from gas that had been barely touched. It carries the chemical signature of a universe that had only just begun to forge its first elements beyond hydrogen and helium. This makes it a population 2 star, a designation astronomers use for old, metal-poor stars typically found in the halo of our galaxy rather than in the disk, where younger, metal-rich stars like the sun reside. And there is another clue that Methuselah is ancient. It is moving fast, remarkably fast. While most stars in our solar neighborhood drift along at relatively modest speeds, following the general rotation of the Milky Way's disk, Methuselah tears through the local stellar population at several hundred kilometers per second. It is on a highly elongated orbit that plunges through the galactic disk, and arcs far out into the halo. This kind of orbit is characteristic of the galaxy's oldest residents, stars that formed before the disk itself had fully assembled. When the young Milky Way was still a chaotic cloud of gas and dark matter pulling itself together. These halo stars don't share the orderly circular motion of disk stars. They move on wild, eccentric paths, passing through the disk like travelers passing through a town that was built long after they started their journey. So everything about Methuselah screams old, its chemistry says old, its orbit says old, its position in stellar evolution says old. The question was never whether this star was ancient. The question was, how ancient? Methuselah has been studied for well over a century. It first appeared in the Henry Draper Catalogue, a massive survey of stellar spectra compiled at Harvard College Observatory in the early 1900s. At the time, it was simply one entry among hundreds of thousands. There was no reason to single it out, but over the following decades, as astronomers developed better tools for analyzing starlight and began classifying stars by their chemical composition, HD 140,283 started standing out. Its extreme metal poverty made it unusual. Its high velocity made it interesting. And as the concept of stellar populations took shape in the 1940s, thanks to the work of astronomer Walter Badeau, who recognized that the Milky Way contains distinct populations of stars with different ages and chemical properties, Methuselah became a key object of study. It was a textbook example of a population 2 halo star, one of the oldest objects accessible to detailed observation. By the late 20th century, astronomers had the tools to attempt something remarkable. They could try to calculate Methuselah's age directly. Not just say it's old, not just say it's ancient, but put an actual number on it. And this is where the trouble began. The age estimates that emerged in the late 1990s and early 2000s were unsettling. Different research groups, using slightly different methods and slightly different input data, kept arriving at numbers that hovered around 14 to 16 billion years. Some estimates were as high as 16 billion, others clustered near 14.5 billion, but nearly all of them exceeded 13.8 billion, the accepted age of the universe, and that was a problem. The age of the universe is not a rough guess. It is one of the most precisely measured quantities in all of cosmology. The number comes from multiple independent lines of evidence that all converge on the same answer. And understanding why that number is so firm is crucial to understanding why Methuselah's age estimate was so alarming. The primary tool for measuring the age of the universe is the cosmic microwave background, a faint glow of radiation that fills all of space. This radiation is the afterglow of the Big Bang itself. When the universe was very young, less than about 400,000 years old, it was so hot and dense that matter and light were tangled together in a blinding fog. Photons couldn't travel freely because they kept colliding with charged particles. The universe was opaque, like the inside of a furnace. But as the universe expanded, it cooled. Eventually, it cooled enough for electrons to combine with protons and form neutral hydrogen atoms. At that moment, the fog cleared. Photons were suddenly free to travel. They streamed outward in every direction and have been traveling ever since, for nearly 14 billion years, crossing the expanding universe, stretching to longer and longer wavelengths as space itself stretched. Today, those photons reach us as faint microwave radiation, with a temperature of about 2.7 degrees above absolute zero. This cosmic microwave background was first detected in 1965 by Arno Penzias and Robert Wilson, who stumbled onto it while working with a radio antenna in New Jersey. They couldn't figure out where the persistent hiss in their instrument was coming from. They cleaned pigeon droppings off the antenna. They checked every cable and connection. Nothing helped. The hiss was always there, coming from every direction in the sky equally. Eventually, they realized they were hearing the faint echo of the universe's birth. That discovery earned them the Nobel Prize. Since then, a series of increasingly sophisticated space missions have mapped the cosmic microwave background in extraordinary detail. The Cosmic Background Explorer, launched in 1989, confirmed that the radiation has a perfect thermal spectrum, exactly matching the prediction of a hot, dense early universe that has been cooling as it expands. The Wilkinson Microwave Anisotropy Probe, launched in 2001, measured tiny temperature fluctuations in the background radiation, variations of about 1 part in 100,000, which represent the seeds of all the structure in the universe today. Galaxies, clusters, superclusters, the entire cosmic web grew from those tiny ripples. And the Planck satellite, launched in 2009, refined those measurements to extraordinary precision. By analyzing the pattern of fluctuations, their sizes, their amplitudes, their statistical relationships, cosmologists could extract the fundamental parameters of the universe, including its age. The answer from Planck's final data release, it's 13.787 billion years, plus or minus about 20 million years. That uncertainty is tiny. We know the age of the universe to within about 0.1%. This isn't a ballpark figure, it's a measurement, and there are independent checks. The expansion rate of the universe, measured by observing how fast distant galaxies are receding from us, gives a consistent age. The abundances of the lightest elements, hydrogen, helium, and lithium, produced in the first few minutes after the Big Bang, match predictions based on the same age. The distribution of galaxy clusters across space fits models built on the same timeline. Everything converges. The age of the universe is not in serious dispute. 13.8 billion years. That is the budget of cosmic time. Everything that exists must fit within it. So when a research team calculates that a single star is 14.5 billion years old, there is no comfortable place to put that number. It doesn't fit. It can't fit. 13.8 billion years is the hard ceiling. The universe cannot contain objects older than itself. For the same reason a house cannot contain rooms that were built before the foundation was laid. If the star is truly older than the cosmos, then either the star's age is wrong, or the universe's age is wrong. There is no third option. And here is why this wasn't just an academic oddity. Astronomers can tolerate uncertainty. They deal with it every day. Measurements have error bars. Models have assumptions. Data has noise. A result that's a little bit off doesn't necessarily alarm anyone. But the Methuselah problem was different because it directly pitted two of astronomy's most important achievements against each other. On one side, you had the age of the universe derived from precision cosmology, backed by space missions costing billions of dollars, confirmed by multiple independent methods, and refined over decades of painstaking observation. This was some of the most robust science in existence. The cosmic microwave background measurements aren't ambiguous. The data is clean, the physics is well understood, and the results are reproducible. Challenging the age of the universe would mean something was fundamentally wrong with our understanding of cosmology itself. On the other side, you had stellar age estimation, a mature field with a long track record, built on well-tested models of nuclear physics and stellar evolution. Astronomers have been calculating the ages of stars for decades. The methods work. They've been validated against star clusters where all the stars formed at the same time, providing a natural cross-check. When you apply these methods to well-studied clusters, you get consistent, sensible results. The science is sound. Both pillars of modern astrophysics were telling the truth as best they could. And yet, their answers contradicted each other. Something had to give. This is why the Methuselah paradox mattered. It wasn't a curiosity tucked away in a footnote. It was a direct collision between two of the most fundamental measurements in astronomy. If the star's age was right, then our entire cosmological framework, the Big Bang, the expansion history, the cosmic microwave background, all of it needed to be reconsidered. And if the star's age was wrong, then something was off in how we estimate stellar ages, which would have ripple effects across every study that relies on those methods. Either way, something important was broken. Either way, the resolution would teach us something profound about how the universe works and about the limits of what we think we know. The paradox sat at the center of modern astrophysics, like a splinter. You couldn't ignore it. You couldn't explain it away with a shrug. You had to find the mistake. The star was real. It was sitting right there, 190 light years away, visible through binoculars. The number was real too, published in peer-reviewed journals, reproduced by independent teams. Both the star and the number existed. So where was the error hiding? To answer that, we need to understand exactly how astronomers calculate the age of a star in the first place, and why this particular star's age was so sensitive to the inputs that went into the calculation. Because the answer, when it finally came, was not that anyone made a blunder. It was subtler and more instructive than that. The mistake was hiding inside the uncertainties themselves, in the small gaps between what we measured and what we assumed, in the difference between a number and the confidence we place in that number. The resolution would come not from a single dramatic discovery, but from a patient, methodical effort to sharpen every measurement, tighten every assumption, and trace every source of error back to its origin. It would take years. It would require space telescopes, revised chemical analyses, and updated models of stellar physics. And when it was finished, the answer would be just as remarkable as the paradox itself, because Methuselah would turn out to be extraordinarily old. Not older than the universe, but close enough to its edge that the star becomes something arguably more amazing than the paradox ever was. A survivor from the cosmic dawn, a relic of the first billion years, a piece of the infant universe still burning in our sky. But before we can get to the resolution, we have to understand the machinery. We have to look inside the calculations and see exactly how astronomers weigh the years of a star, and why that process, for all its sophistication, left enough room for a number like 14.5 billion to slip through. So how do you figure out how old a star is? You can't cut it open and count rings like a tree. You can't ask it. You can't look up its birth certificate. A star is a ball of plasma burning trillions of miles away, and the only information it sends you is light. That's all you have. Photons. A faint stream of electromagnetic radiation crossing the void of space to reach your telescope. Everything astronomers know about a star, its temperature, its size, its chemical composition, its age, all of it must be extracted from that light. And extracting an age is one of the hardest things you can do. The fundamental tool for understanding stellar ages is something called the Hertzsprung-Russell diagram. It was developed independently in the early 1900s by two astronomers, the Danish astronomer I. Nar Hertzsprung and the American astronomer Henry Norris Russell. The concept behind it is deceptively simple. You take a star, you measure two things about it, its surface temperature and its luminosity, and you plot it on a graph. Temperature goes on one axis, luminosity on the other. That's it. Two numbers, one dot on a chart. But the power of this diagram is extraordinary. When you plot thousands of stars on it, patterns emerge. Stars don't scatter randomly across the chart. They cluster along specific bands and regions. The most prominent feature is a long diagonal stripe, running from the upper left corner, where hot, luminous stars live, down to the lower right, where cool, dim stars reside. This stripe is the main sequence, and it represents stars in the prime of their lives, steadily fusing hydrogen into helium in their cores. Our sun sits on the main sequence. Most of the stars you see in the night sky sit on the main sequence. A star spends the vast majority of its life here, and while it's on the main sequence, it barely changes. It just burns, decade after decade, century after century, billion years after billion years, in a state of near-perfect equilibrium. But stars don't stay on the main sequence forever. Eventually, the hydrogen fuel in the core runs out. When that happens, the star's internal balance shifts. The core contracts under gravity because there's no longer enough outward pressure from fusion to hold it up. As the core contracts, it heats up. The layers of hydrogen surrounding the core get hot enough to start fusing, and this shell burning causes the outer layers of the star to expand and cool. The star swells, it brightens, it moves off the main sequence on the diagram, drifting upward and to the right, toward the region occupied by red giants. This transition is the key to stellar age determination. While a star is sitting on the main sequence, barely changing, it's very hard to tell how old it is. A star that's been burning for 3 billion years looks almost identical to one that's been burning for 8 billion years, at least from the outside. The differences are subtle, buried deep in the core where you can't observe them directly. But the moment a star begins leaving the main sequence, its observable properties start changing in ways that depend sensitively on how long it's been burning. The star's position on the Hertzsprung-Russell diagram during this transition phase carries a timestamp. And this is where ISOC-Rohn fitting comes in. An ISOC-Rohn is a theoretical curve on the Hertzsprung-Russell diagram that represents a snapshot of where stars of different masses should be at a single specific age, assuming they all have the same chemical composition. The word comes from the Greek for equal time. Imagine you could create 1 million stars simultaneously, all with the same chemical makeup but with different masses. Some would be massive and burn hot. Others would be small and burn cool. You let them all evolve for, say, 10 billion years. At the end of that time, you plot all of them on the Hertzsprung-Russell diagram. The resulting curve is the 10 billion year ISOC-Rohn for that chemical composition. Different ages produce different curves. A 5 billion year ISOC-Rohn looks different from a 10 billion year one, which looks different from a 13 billion year one. The differences are most dramatic near the turnoff point. The spot on the diagram where the ISOC-Rohn peels away from the main sequence. In a young population of stars, the turnoff point is high up and to the left. Because only the very massive, very hot stars have had time to exhaust their fuel and leave the main sequence. In an old population, the turn-off point is lower, and to the right, because even less massive, cooler stars have had time to run through their hydrogen and begin transitioning. The older the population, the lower the turn-off. This is elegant and powerful. You observe a star, measure its temperature and luminosity, check its chemical composition, and then you compare its position on the diagram against a library of theoretical ISOC rones. You find the one that passes through the star's observed position. The age of that ISOC rone is your estimate for the age of the star. In practice, this works best for stars that are near the turn-off point or just past it, in the subgiant phase. And that is exactly where Methuselah sits. It has recently left the main sequence and is beginning its transition toward the red giant branch. This makes it, in principle, an ideal candidate for age determination. Its position on the diagram is exquisitely sensitive to age. Now, you might reasonably ask how astronomers know this method actually works. It sounds elegant in theory, but theory is not the same as a reality. How do you verify that ISOC rone fitting gives you the right age when you can't exactly check a star's birth certificate? The answer lies in one of nature's most useful gifts to astronomers: globular clusters. A globular cluster is a dense, roughly spherical collection of stars bound together by gravity. The Milky Way has about 150 known globular clusters, and they are among the oldest structures in our galaxy. A typical globular cluster contains anywhere from 100,000 to over 1 million stars packed into a volume only a few dozen light years across. To the naked eye, the closest ones look like faint fuzzy patches. Through a telescope, they resolve into dazzling swarms of individual stars, so densely concentrated toward the center that they blur into a continuous glow of light. What makes globular clusters invaluable for stellar age science is a simple but powerful fact. All the stars in a given cluster formed at roughly the same time, from the same cloud of gas, with the same chemical composition. They are siblings. They share a birthday and a chemistry. The only thing that differs from star to star within a cluster is mass. Some stars were born massive, others were born small, and because massive stars burn their fuel faster, they leave the main sequence sooner, while less massive stars remain on the main sequence longer. This means that when you plot all the stars in a globular cluster on a Hertzsprung Russell diagram, you don't get a random scatter. You get a very specific shape. The lower mass stars, which haven't yet exhausted their fuel, still sit on the main sequence. The higher mass stars, which have already burned through their hydrogen, have moved off to the right and upward, becoming subgiants and red giants. And connecting these two groups is the turn-off point, the precise spot where the main sequence bends away, marking the boundary between stars that are still burning hydrogen in their cores and stars that have just finished doing so. The location of that turn-off point is a direct clock. In a young cluster, the turn-off is high up and to the left, because only the heaviest, hottest stars have had time to exhaust their cores. In an old cluster, the turn-off is lower and to the right, because even relatively modest stars have used up their hydrogen. The older the cluster, the lower the turn-off. You measure where the turn-off falls, overlay your library of theoretical ISOC rones, and the one that matches gives you the age. And because every star in the cluster has the same age and composition, you're not relying on a single data point. You have thousands of stars tracing out the same curve. The statistics are far more powerful than anything you can do with a single isolated star. This is where the method proves itself. Globular clusters provide a controlled experiment. You can test whether the ISOC rones predicted by stellar evolution models actually match the shapes traced out by real stars of known common origin. And overwhelmingly, they do. The models reproduce the observed cluster sequences with impressive fidelity. The main sequence, the turnoff, the subgiant branch, the red giant branch, all the features predicted by the theory show up in the real data, in the right places, with the right relative numbers of stars at each stage. This is not a coincidence. It means the underlying physics in the models, the nuclear reaction rates, the energy transport mechanisms, the equations of stellar structure is fundamentally correct. One cluster is particularly relevant to the Methuselah story. M92, a globular cluster in the constellation Hercules, is one of the most metal-poor clusters known in the Milky Way. Its iron to hydrogen ratio is roughly negative 2.3, very close to Methuselah's value of negative 2.4. In chemical terms, M92's stars and Methuselah are near cousins. They formed from similarly pristine material in the early universe. When astronomers measured the age of M92 by fitting ISOC rones to its main sequence turnoff, the results consistently come out in the range of 12 to 14 billion years, depending on the specific models and input data used. This is strikingly similar to the range of age estimates for Methuselah. The two approaches, cluster turnoff fitting and individual star ISOC rone fitting, are pointing in the same direction. Both say these metal-poor objects are extremely old, among the oldest things in the galaxy, and both have wrestled with the same uncomfortable fact, that their age estimates sometimes push uncomfortably close to, or even above, the age of the universe. This consistency is actually reassuring, even though it deepens the puzzle in the short term. If Methuselah's absurdly high age were a fluke, an artifact of some unique error specific to that one star, you wouldn't expect globular clusters with similar chemistry to produce similar ages. But they do. M92, NGC6397, M15, multiple ancient metal-poor clusters all return ages in the same general range. The method isn't broken, it's giving consistent answers. The problem, if there is one, lies in the inputs, the distances, the compositions, the model assumptions, not in the fundamental approach. This is why astronomers took the Methuselah paradox seriously rather than dismissing it as a modeling artifact. The ISOC rone method had been validated against globular clusters containing hundreds of thousands of stars. It worked. It produced self-consistent results across different clusters with different compositions. The underlying physics was sound. So when that same well-tested method, applied to a well-studied individual star, produced an age that exceeded the age of the universe, the scientific community couldn't simply shrug it off. The method had earned credibility. Its uncomfortable answer demanded a careful, honest investigation into where the uncertainties lay and how they might be pushing the result in the wrong direction. And that investigation, as we're about to see, would ultimately focus not on the method itself, but on three critical inputs that feed it: the star's temperature, its chemical composition, and above all, its distance. The ISOC rone fitting method is only as good as those three inputs, and each one carries its own uncertainty. If any of them is off, the age comes out wrong. If any of them is off, the age comes out wrong. And the age of a subgent is so sensitive to these inputs that even small errors can produce enormous shifts in the final number. Let's start with surface temperature. Astronomers measure a star's surface temperature by analysing the detailed shape of its spectrum, the rainbow of light it emits. A hotter star emits more blue light. A cooler star emits more red light. The overall shape of the spectrum, combined with the presence and strength of specific absorption lines, reveals the surface temperature to a precision of roughly 50 to 100 degrees in good cases. For Methuselah, the surface temperature has been measured at roughly 5,750 degrees Kelvin, give or take about 50 degrees. That sounds precise, and it is, relatively speaking. But in ISOC Rohn fitting, even 50 degrees of uncertainty in temperature translates into a shift in age. The ISOC Rohns for old, metal-poor stars are spaced closely together on the diagram. Moving the star's position slightly to the left or right, corresponding to a slightly hotter or cooler temperature, can slide it from one ISOC Rohn to another, changing the inferred age by hundreds of millions of years. Temperature is important, but for Methuselah, it wasn't the primary source of trouble. The bigger issues lay elsewhere. Now let's talk about chemical composition, because this is where things get more complex. A star's chemistry affects how it evolves. Heavier elements in a star's gas act as a source of opacity, meaning they make the gas less transparent to radiation. When gas is more opaque, energy takes longer to escape from the star's interior. This changes the internal temperature structure, the rate of nuclear reactions, and ultimately the speed at which the star evolves. Two stars with identical masses but different chemical compositions will evolve at different rates and reach the subgiant phase at different ages. For the ISOC Rohn method to work, you need to know the star's chemical composition as accurately as possible. The standard shorthand astronomers use is the iron to hydrogen ratio, which expresses how much iron the star contains relative to hydrogen compared to the sun's ratio. Iron is used as a proxy for overall heavy element content because it has many strong, easily measurable absorption lines in a star's spectrum. Methuselah's iron to hydrogen ratio is extremely low, roughly negative 2.4 on the logarithmic scale astronomers use. That means it has about 1/250th the iron content of the Sun. This places it among the most metal-poor stars known in the solar neighborhood. But iron isn't the whole story. Other elements matter too, sometimes more than iron. The alpha elements, which include oxygen, magnesium, silicon, calcium, and titanium, are produced by different nuclear processes than iron and can be enhanced relative to iron in old, metal-poor stars. Oxygen, in particular, is critical. Oxygen is one of the most abundant heavy elements in any star, and it contributes significantly to the overall opacity. If you underestimate a star's oxygen content, you underestimate its opacity, and your ISOC Rohn model will predict the wrong evolutionary speed. The star's age will come out wrong. And here's the problem. Measuring oxygen abundance in a metal-poor star is very difficult. The oxygen lines in the spectrum are weak and blended with other features. Different measurement techniques can give different answers. For years, the oxygen abundance used in Methuselah's age calculations carried a real uncertainty that translated directly into uncertainty in the final age. A higher oxygen abundance would mean higher opacity, which would slow the star's evolution. making it younger than a low oxygen model would predict. Getting the oxygen right was crucial, and for a long time, it wasn't nailed down. But the single most important input, the one that dominates everything else in this particular calculation, is luminosity. Luminosity is the total amount of energy a star emits per second. It determines where the star sits vertically on the Hertzsprung-Russell diagram. And for a subgiant like Methuselah, the luminosity is the make or break number. Here is why. When a star leaves the main sequence and enters the subgiant phase, its luminosity increases. It gets brighter, but the rate at which it brightens depends on its age. An older subgiant has been burning longer, its core is more depleted, and it sits at a slightly different luminosity than a younger subgiant of the same temperature and composition. On the Hertzsprung-Russell diagram, the ISOC rones for old, metal-poor stars are almost horizontal in the subgiant region. They're nearly flat lines, stacked very close together. This means that a small change in luminosity, shifting the star slightly up or down on the diagram, can jump it from one ISOC rone to another, dramatically changing the inferred age. A subgiant's age is exquisitely sensitive to its luminosity. If you get the luminosity even slightly wrong, the age can swing by 1 billion years or more. And this brings us to the real heart of the problem. You cannot measure a star's luminosity directly. What you actually measure is its apparent brightness, how bright it looks from Earth. But apparent brightness depends on two things: how much light the star actually emits, its true luminosity, and how far away it is. A very luminous star that's very far away can look just as bright as a dimmer star that's closer. To convert apparent brightness into true luminosity, you need to know the distance. Distance is everything. Distance is the foundation of the entire calculation. Get the distance wrong, and the luminosity is wrong. Get the luminosity wrong, and the position on the diagram is wrong. Get the position on the diagram wrong, and the age is wrong. Every error in distance ripples upward through the calculation, amplified at each step, until it lands in the final age estimate as a potentially enormous uncertainty. So, how do astronomers measure the distance to a star? The most direct method is parallax. Parallax is the apparent shift in a star's position against the background of much more distant stars as Earth orbits the Sun. Think of it this way. Hold your thumb out at arm's length and close one eye. Note where your thumb appears against the background. Now, switch eyes. Your thumb seems to jump to a different position. That apparent shift is parallax, caused by the change in your viewing angle as you switch from one eye to the other. Astronomers do the same thing with stars, but instead of switching eyes, they use the motion of Earth around the Sun. In January, Earth is on one side of its orbit. In July, it's on the opposite side, about 300 million kilometers away from where it was 6 months earlier. As Earth moves, nearby stars appear to shift slightly against the background of very distant stars, which are so far away they don't seem to move at all. By measuring this tiny shift, astronomers can calculate the star's distance using simple geometry. The closer the star, the larger the shift. The farther the star, the smaller the shift. This sounds straightforward, and conceptually it is, but the actual shift involved are fantastically small. Even for the nearest stars, the parallax angle is less than 1 arcsecond, which is 1/3600th of a degree. For a star like Methuselah, roughly 190 light-years away, the parallax angle is about 17 milliseconds, That is 17 thousandths of 1 arcsecond. To give you a sense of how small that is, 1 millisecond is roughly the angular size of a coin seen from a distance of about 3,700 kilometers. You're trying to measure shifts so tiny that they push the absolute limits of your instruments. For most of the 20th century, parallax measurements were made from the ground, using photographic plates and careful astrometric techniques. These measurements were heroic efforts, but the atmosphere blurs starlight, limiting precision to maybe 10 or 20 milliseconds at best. For a star like Methuselah, that meant the distance was known only roughly, and the uncertainty in the distance fed directly into the uncertainty in the luminosity, which fed into the uncertainty in the age. Then, in 1989, the European Space Agency launched Hipparcos, the first space mission dedicated to precision astrometry. Orbiting above the atmosphere, Hipparcos could measure stellar positions with a precision of about 1 to 2 milliseconds, a dramatic improvement over ground-based work. Hipparcos measured the parallax of HD 140,283 and got a value of about 17.44 milliseconds, with an uncertainty of about 0.97 milliseconds. That translates to a distance of roughly 187 light-years, give or take about 10 light-years. This was a good measurement by the standards of the 1990s, but notice the uncertainty. Roughly 1 millisecond of uncertainty in the parallax corresponds to roughly 10 light-years of uncertainty in the distance. That 10 light-years of distance uncertainty translates into an uncertainty in luminosity. And because the ISOC rones are packed so tightly together in the subgiant region, that luminosity uncertainty translates into an age uncertainty of roughly 2 billion years or more. This is the critical point. The early age estimates of 14 to 16 billion years for Methuselah were not made carelessly. They used the best data available at the time. They used standard, well-tested methods. The researchers knew there were uncertainties. They reported error bars. A typical result might have been somewhere around 14.5 billion years, with uncertainties spanning roughly 1 billion years in either direction. The central value was above the age of the universe, but the lower end of the error range did dip below 13.8 billion. So the result was uncomfortable rather than flatly impossible. If you squinted at the error bars, you could argue there was no real contradiction, but the central value, the best estimate, the number that the data pointed to most strongly, was still on the wrong side of the line. And that central value kept showing up in study after study from different groups using slightly different approaches. The star kept coming out too old. The problem was not a single blunder, it was the accumulation of multiple small uncertainties, each individually reasonable, each individually within the normal range for astronomical measurements, but all conspiring in the same direction. The distance was uncertain, the oxygen abundance was uncertain. The stellar evolution models had their own assumptions about physics, nuclear reaction rates, how elements settle within a star over billions of years, how energy is transported from core to surface, and each of those assumptions introduced additional uncertainty. None of these uncertainties were scandalous. They were all normal, expected, well documented. But when you stack them together, they add up. Imagine measuring the length of a table using a ruler that's accurate to within half a centimeter. You measure the width with a different ruler, also accurate to within half a centimeter. You measure the height with a third ruler, same accuracy. Each measurement is fine on its own, but when you multiply all three to calculate the table's volume, the uncertainties compound. The final answer has a larger uncertainty than any individual measurement. The same thing happened with Methuselah. Each input, distance, temperature, composition, carried its own error bar. And when those inputs were combined through the eye-sock Roan fitting machinery to produce an age, the uncertainties multiplied and reinforced each other, producing a final age estimate with an error bar large enough to span the gap between 13 and 15 billion years. What made the situation especially vexing was the asymmetry of the sensitivity. The subgiant region of the Hertzsprung-Russell diagram, where Methuselah sits, is where small changes in luminosity produce the largest changes in age. This is not true for all stars. A star sitting squarely on the main sequence is relatively insensitive to luminosity changes because the ISOC Roans run nearly vertically there, meaning age differences show up as temperature differences, not luminosity differences. But in the subgiant region, the ISOC Roans flatten out. They run nearly horizontally. Luminosity becomes the dominant variable. And because luminosity depends on distance squared, any error in distance is squared before it enters the age calculation. A 5% error in distance becomes a 10% error in luminosity, which can become a billion-year error in age for a star in this particular evolutionary stage. This is why Methuselah was such a perfect storm. The star happened to be at the exact evolutionary stage where age sensitivity is maximized. It happened to be at a distance where parallax uncertainties were significant. It happened to have a chemical composition that was difficult to characterize precisely, especially regarding oxygen. And it happened to be so old that the age of the universe itself was within the error bars. Any other star, at any other evolutionary stage, at any other distance, with any other composition, might have produced an age estimate that was uncertain but unremarkable. Methuselah combined every possible source of sensitivity into one object. Astronomers understood all of this. They knew the paradox was almost certainly an artifact of measurement uncertainty, rather than a real violation of cosmology. The error bars were large enough to permit the star to be younger than the universe. Nobody seriously believed the star predated the Big Bang, but understanding that the paradox was likely a measurement issue and actually resolving it are two very different things. To resolve it, you needed better measurements. You needed a more precise distance. You needed better chemical abundances. You needed improved stellar evolution models with updated physics. You needed to tighten every input until the error bars shrank enough that the age came firmly below 13.8 billion years. And that effort would take more than a decade. The Methuselah paradox wasn't a mystery about a magical star. It was a mystery about precision. It was a story about the difference between a measurement and a fact, about the gap between what your data says and what reality is, and about the painstaking work required to close that gap. The star was never older than the universe, but proving that rigorously and quantitatively required pushing the limits of observational astronomy and stellar physics in ways that would ultimately make our understanding of stars and their ages sharper than it had ever been before. Resolving the Methuselah paradox was not a single eureka moment. There was no dramatic night at the telescope where someone looked through the eyepiece and suddenly saw the answer. Instead, the resolution came slowly, methodically, across more than a decade of patient work on multiple fronts. Different teams attacked different pieces of the problem. One group, improve the distance measurement. Another refined the chemical analysis. Others updated the physics inside the stellar evolution models themselves. Each improvement, taken alone, nudged the age downward by a modest amount. But taken together, they transformed an impossible number into a remarkable but physically plausible one. The paradox dissolved, not with a bang, but through the quiet, grinding progress of precision science. The first and most impactful correction came from the distance. As we explored, the Hipparcos satellite measured Methuselah's parallax in the early 1990s and obtained a value of approximately 17.44 milliarc seconds, with an uncertainty of about 0.97 milliarc seconds. That uncertainty was the root of the problem. It translated into roughly a 5.5% error in distance, which became roughly an 11% error in luminosity, which ballooned into an age uncertainty of nearly 2 billion years once it passed through the ISOC Roan fitting machinery. The measurement was good by 1990s standards, but it wasn't good enough to resolve a paradox operating at the billion-year scale. To fix this, astronomers turned to the Hubble Space Telescope. Hubble is famous for its stunning photographs of galaxies and nebulae, but it also carries an instrument called the Fine Guidance Sensors. These sensors were originally designed to lock the telescope onto guide stars and hold it steady during observations. But astronomers realized they could also be used for extremely precise astrometry, measuring the positions of stars with a precision far beyond what Hipparcos could achieve. The fine guidance sensors measure the position of a target star relative to reference stars in the same field, tracking tiny shifts as Earth orbits the Sun. Because Hubble sits above the atmosphere, there is no atmospheric blurring. The measurements are clean, sharp, and repeatable. A team led by astronomer Howard Bond launched a dedicated campaign to measure Methuselah's parallax using Hubble's fine guidance sensors. They observed the star repeatedly over several years, carefully tracking its apparent motion against distant background reference stars. Each observation captured the star's position at a different point in Earth's orbit, building up a detailed record of the parallax shift. The campaign demanded extraordinary care. The reference stars themselves had to be characterized precisely. Systematic effects in the instrument had to be modeled and removed. Every source of potential error had to be identified, quantified, and either corrected or included in the final uncertainty budget. The result, published in 2013, was transformative. The new parallax came out to approximately 17.15 milliarc seconds, with an uncertainty of just 0.14 milliarc seconds. Compare that to Hipparcos. The central value shifted slightly, from 17.44 to 17.15. That shift was small but meaningful, corresponding to a change in distance from roughly 187 light years to roughly 190 light years. The star was slightly farther away than Hipparcos had indicated. A slightly greater distance means a slightly higher luminosity, because to appear the same brightness from farther away, the star must be intrinsically brighter, and a slightly higher luminosity shifts the star's position on the Hertzsprung-Russell diagram, placing it on a different ISOC Roan. But the real breakthrough was the precision. The uncertainty shrank from 0.97 milliarc seconds to 0.14 milliarc seconds, a factor of nearly 7. The fractional error in the parallax dropped from about 5.5% to less than 1%. That translated into a fractional error in luminosity of less than 2%. which translated into an age uncertainty from the distance alone of roughly 700 million years, instead of nearly 2 billion. The single largest contributor to the age uncertainty had been dramatically reduced. The error bars had been squeezed. With this improved parallax alone, the age estimate shifted slightly, but the central value still hovered uncomfortably high. The distance improvement helped, but it wasn't enough by itself. The other inputs needed tightening too. The second major correction came from the chemical composition, specifically from oxygen. Oxygen is the third most abundant element of the universe, after hydrogen and helium. In a star like Methuselah, which is extremely poor in heavy elements overall, oxygen makes up a disproportionately large fraction of whatever heavy elements are present. This matters because oxygen is a significant source of opacity inside a star. Opacity, in the context of stellar physics, describes how easily radiation can travel through the star's gas. Higher opacity means radiation gets absorbed and re-emitted more often as it works its way outward from the core to the surface. This slows down the transport of energy and changes the star's internal temperature structure, which in turn changes how quickly the star evolves. For ISOC-Rohn fitting, the total heavy element content of the star is a critical input. If you underestimate the oxygen abundance, you underestimate the total opacity, and your model predicts that the star evolves more slowly than it actually does. A slower evolving model requires more time to reach the observed subgiant stage, so the inferred age comes out older. Conversely, if the true oxygen abundance is higher than assumed, the star has higher opacity, evolves faster, and is younger than the initial calculation suggested. Measuring oxygen in a metal-poor star like Methuselah is notoriously difficult. The most commonly used oxygen indicators in stellar spectra are absorption lines that are either very weak, heavily blended with other features, or sensitive to modeling assumptions about the star's atmosphere. Different spectroscopic techniques yielded different answers. Some studies used the forbidden oxygen line at 6,300 angstroms. Others used ultraviolet hydroxyl bands. Others used the oxygen triplet at 7,700 angstroms, which is strong but highly sensitive to departures from a simplifying assumption called local thermodynamic equilibrium. Over the years following the initial age estimates, several teams conducted careful reanalyses of Methuselah's oxygen abundance using improved spectroscopic data and more sophisticated atmospheric models. The results consistently pointed to a higher oxygen to iron ratio than earlier work had assumed. The star was enhanced in oxygen as expected for an old, metal-poor halo star whose heavy elements came primarily from core collapse supernovae, which produce relatively more oxygen than iron compared to other types of stellar explosions. When this higher oxygen abundance was fed into the ISOC-Rohn models, the effect was significant. Each incremental increase in the assumed oxygen content pushed the age downward, because higher oxygen meant higher opacity, which meant faster evolution, which meant less time needed to reach the observed subgiant state. The oxygen correction alone accounted for a reduction of several 100 million years in the inferred age. The third major correction came from the nuclear physics inside the stellar evolution models themselves. Stellar evolution models are essentially computer simulations that track a star's life from birth to death. They calculate how the star's internal structure changes over time as nuclear fuel is consumed, as energy is transported from the core to the surface, and as the star's outer layers respond to changes in the core. These models are built on fundamental physics, nuclear reaction rates, thermodynamics, fluid dynamics, radiative transfer, but many of the inputs are themselves measured quantities with their own uncertainties. One of the most important nuclear reactions for stellar age estimates is a proton capture reaction that serves as the bottleneck of the carbon-nitrogen-oxygen cycle. The carbon-nitrogen-oxygen cycle is a sequence of nuclear reactions that converts hydrogen into helium using carbon, nitrogen, and oxygen nuclei as catalysts. In hot, massive stars, the carbon-nitrogen-oxygen cycle dominates energy production. In cooler, lower mass stars like Methuselah, the simpler proton-proton chain is the primary energy source, and the carbon-nitrogen-oxygen cycle plays a secondary role. But even in metal-poor stars, where the carbon-nitrogen-oxygen cycle contributes only a small fraction of the total energy, the rate of its bottleneck reaction affects the overall calibration of stellar models, and therefore influences age estimates. For decades, the rate of this critical reaction was measured in laboratory experiments at relatively high energies, and then extrapolated downward to the much lower energies relevant inside stellar cores. This extrapolation introduced significant uncertainty. Then, in the early 2000s, physicists at the Laboratory for Underground Nuclear Astrophysics, a facility buried deep beneath the Gran Sasso mountain in Italy, managed to measure the reaction rate at energies much closer to those found in actual stellar interiors. The laboratory's location underground shielded the experiment from cosmic rays, which would otherwise overwhelm the faint signals from nuclear reactions at such low energies. Then, in the early 2000s, physicists found a way to do something remarkable. They went underground, deep underground. The Laboratory for Underground Nuclear Astrophysics sits inside the Gran Sasso mountain in the Apennine range of central Italy, buried beneath roughly 1,400 meters of solid rock. To reach it, you drive through a highway tunnel that cuts through the mountain, then turn off into a side passage that leads to a set of caverns carved out of the stone. Down there, in chambers that look more like a submarine hull than a physics laboratory, researchers built particle accelerators designed to replicate the nuclear reactions that happen inside stellar cores. The reason for going underground is simple but essential. At the Earth's surface, cosmic rays, high-energy particles raining down from space, constantly bombard any detector you build. These cosmic rays produce signals that drown out the extraordinarily faint signatures of nuclear reactions occurring at stellar energies. The reactions physicists needed to measure happen at very low energies, far lower than those in conventional accelerators, and the signals they produce are whisper quiet. At the surface, those whispers are lost in the roar of cosmic ray noise, but 1,400 meters of rock acts as a natural shield, absorbing virtually all incoming cosmic rays. Inside the mountain, the background noise drops by a factor of roughly 1,000,000. The whispers become audible. There is something quietly poetic about this. Understanding the age of a star burning 190 light-years above us required descending deep beneath the surface of the Earth, hiding from the cosmos in order to hear what the cosmos was trying to tell us. In that shielded environment, the lunar team managed to measure the critical reaction rate at energies much closer to those found in actual stellar interiors than any surface laboratory had achieved. The results were surprising. The reaction rate turned out to be roughly half what previous extrapolations had assumed. A slower bottleneck reaction means less energy produced by the carbon-nitrogen-oxygen cycle, which changes the predicted structure of the star and the speed at which it evolves. When stellar evolution models were updated with this new, lower reaction rate, the predicted ages of old metal-poor stars shifted downward. The change was not enormous for a star like Methuselah, where the carbon-nitrogen-oxygen cycle is subdominant, but it was measurable. It contributed another slice of the overall age reduction, shaving off roughly 100 to 300 million years, depending on the specific models used. Other nuclear reaction rates were also updated during this period. The rates of key steps in the proton-proton chain, the dominant energy source in stars like Methuselah, were refined through new laboratory measurements. Each update slightly modified the predicted evolutionary tracks, and each modification fed into the age calculation. No single update was revolutionary. Each was a modest correction. But like a sculptor refining a form through small, careful strokes, the cumulative effect was substantial. The fourth major correction involved a physical process that had been neglected in many earlier stellar models: the gravitational settling of helium. Inside a star, the gas is not perfectly uniform. Over billions of years, gravity slowly pulls heavier atoms downward toward the core, while lighter atoms drift upward toward the surface. Helium, being about 4 times heavier than hydrogen, gradually sinks. Hydrogen, being lighter, floats upward. This process is called diffusion, or gravitational settling, and over the lifetime of a star like Methuselah, which has been burning for well over 12 billion years, the effect is significant. The surface layers become slightly enriched in hydrogen and slightly depleted in helium compared to the original composition. The core, meanwhile, becomes slightly enriched in helium beyond what nuclear fusion alone would produce. Earlier generations of stellar evolution models often ignored diffusion entirely or treated it in simplified ways. The effect was known in principle, but was computationally expensive to include, and was considered a minor refinement rather than a critical correction. For young or middle-aged stars, this was a reasonable approximation. Over a few billion years, the settling is small, but for a star that has been burning for more than 12 billion years, the cumulative effect of diffusion is large enough to change the star's observable properties and therefore its inferred age. Including diffusion in the models changes the picture in a specific way. As helium settles out of the envelope over time, the surface opacity decreases because helium contributes to opacity. This makes the star slightly hotter and slightly more luminous than a model without diffusion would predict for the same age. When you then observe the real star and try to match it to an ISOC Rhone, the ISOC Rhone with diffusion fits the star at a younger age than the ISOC Rhone without diffusion. In other words, including this physical process in the models makes old stars come out younger, because the models account for how the star's surface properties have changed over time due to internal redistribution of elements. The age reduction from including diffusion was roughly 300 to 500 million years for Methuselah. But diffusion itself has complications. Pure gravitational settling, if left unchecked, would predict surface compositions that don't match observations. Something partially counteracts the settling, probably turbulent mixing in the star's outer layers, driven by processes that are not fully understood. Modern models include diffusion but often apply a correction factor to account for this competing turbulence. The exact value of that correction introduces its own uncertainty, which adds to the systematic error budget of the final age. This is an honest complication, and researchers include it in their reported uncertainties rather than pretending it doesn't exist. There was also a fifth strand of improvement: updated opacity tables. Opacity calculations describe how the gas inside a star absorbs and re-emits radiation as a function of temperature, density, and chemical composition. These calculations are enormously complex because they involve contributions from millions of spectral lines of dozens of elements under extreme conditions. Research groups periodically release updated opacity tables incorporating new atomic physics data, improved line broadening calculations, and better treatment of electron scattering. Each update slightly changes the predicted internal structure of stars and therefore the predicted evolutionary tracks. For Methuselah, updated opacity calculations contributed a smaller but still meaningful correction, further refining the age estimate. Now, let's bring all of these improvements together and see what happened to the age. The team led by Howard Bond, in their 2013 study, combined the new Hubble parallax with updated stellar evolution models that included improved chemical abundances, diffusion, and updated nuclear physics. Their initial best estimate for the age, based purely on the statistical fit to the ISOC-Rohn models with the new parallax, came out to approximately 14.46 billion years, plus or minus about 300 million years from statistical uncertainties alone. That central value was still above the age of the universe. But here is the crucial point. When they carefully accounted for all the systematic uncertainties, the oxygen abundance, the nuclear reaction rates, the treatment of diffusion, the opacity tables, the total uncertainty expanded to roughly plus or minus 800 million years. The lower end of that range reached down to about 13.7 billion years, which is just below the age of the universe at 13.8 billion. For the first time, the error bars comfortably included ages younger than the universe. The paradox was no longer a paradox. It was a measurement consistent with the cosmological age limit. But the story didn't end there. Subsequent studies pushed further. Additional spectroscopic campaigns delivered even more refined oxygen and other alpha element abundances. New generations of stellar evolution codes incorporated more sophisticated physics, better diffusion treatments with calibrated turbulent mixing, and the latest nuclear data from underground laboratories. And in the years following Bond's Hubble campaign, the European Space Agency's Gaia satellite began delivering parallax measurements of extraordinary precision for over 1 billion stars. Gaia's measurement of Methuselah's parallax was consistent with the Hubble value, but carried an even smaller uncertainty, confirming the distance to high confidence and removing any lingering worry that the Hubble result might have been affected by instrumental systematics. When all of these improvements were folded together, the best modern estimates for Methuselah's age converged around 12.7 billion years, plus or minus roughly 800 million years. That range spans from about 11.9 billion years at the low end to about 13.5 billion years at the high end. The entire range sits below the age of the universe. The central value is more than 1 billion years younger than the cosmos. The paradox is resolved. But resolved does not mean settled beyond all doubt. It means the measurements and the models are now consistent with each other, and with the cosmological age limit. The error bar of plus or minus 800 million years is real. It reflects genuine remaining uncertainties in the oxygen abundance, in the treatment of diffusion, in the nuclear reaction rates, and in the modeling assumptions that go into the ISOC-ROHN calculations. 800 million years is a long time. It means we know the star's age to within roughly 6%, which is remarkably precise for a measurement this difficult. But it also means there's still room for the true age to be somewhat higher or lower than the central estimate. What should be appreciated is how hard-won this resolution was. The original paradox arose not because anyone made an error, but because the measurements available at the time carried uncertainties large enough to push the age above the cosmological limit. Resolving it required improvements on every front simultaneously. A better parallax alone was not enough. Better chemistry alone was not enough. Better nuclear physics alone was not enough. Better diffusion models alone were not enough. Each improvement contributed a piece. Only when all the pieces came together did the answer land firmly on the right side of the line. And there is something deeply instructive about this. In science, the difference between a paradox and a precise measurement is often just a matter of error bars. Methuselah was never actually older than the universe. The star didn't change. The universe didn't change. What changed was our ability to measure. As the measurements sharpened, the apparent contradiction evaporated. The paradox was real, in the sense that the data genuinely pointed to an impossible answer, but it was a paradox of precision, not a paradox of physics. The universe was consistent all along. We just needed better tools to see it, and even with the paradox resolved, what remains is astonishing. 12.7 billion years. Imagine that number for a moment. The universe itself is only 13.8 billion years old. This star formed when the cosmos was barely a billion years old, possibly younger. The galaxies we see in deep Hubble and Webb images at high redshift, those faint smudges of light from the infant universe, were the kinds of structures being assembled when Methuselah ignited. The first heavy elements had just been forged. The first supernovae had just detonated. The raw material of this star was gas that had been processed through perhaps one generation of stellar life, maybe less. Methuselah carries the chemical memory of the era in its atmosphere. It is not just an old star, it is a fossil. And what that fossil tells us about the universe it was born into is where this story has been heading all along. Methuselah is roughly 12.7 billion years old. The universe is 13.8 billion years old. That means this star ignited when the cosmos was only about 1 billion years old, give or take a few 100 million years in either direction. And that single fact, once you sit with it, is staggering. 1 billion years after the Big Bang, the universe was a radically different place. There were no spiral galaxies with graceful arms and orderly rotation. There were no stable solar systems with rocky planets orbiting at comfortable distances from well-behaved stars. There were no nebulae glowing with the recycled remains of countless stellar generations. The cosmos was young, chaotic, and almost entirely dark. The first structures were only beginning to emerge from a fog of cooling hydrogen and helium, pulling together under gravity into clumps that would eventually become the seeds of galaxies. And somewhere in that turbulent infant universe, in a collapsing cloud of nearly pristine gas, Methuselah was born. To understand what that means, you need to understand the generational structure of stars. Astronomers classify stars into three broad populations based on their chemistry and when they formed. The naming convention is historical and, somewhat confusingly, runs backward. Population 1 stars are the youngest and most metal-rich. Our Sun is a population 1 star. It formed about 4.5 billion years ago from gas that had been enriched by many previous generations of stellar birth and death. Population 1 stars live primarily in the thin disk of spiral galaxies, where gas is dense and star formation is ongoing. They contain relatively high abundances of heavy elements: iron, silicon, oxygen, carbon, all the products of billions of years of cosmic chemistry. Population 2 stars are older and metal poor. They formed early in the universe's history, when the available gas had been processed through only 1 or 2 cycles of stellar evolution. Their heavy element content is much lower than population 1 stars, sometimes hundreds or thousands of times lower than the Sun's. Population 2 stars are found in the halos of galaxies, in globular clusters, and in the thick disk. They move on eccentric, often highly inclined orbits that reflect the chaotic dynamics of the early galaxy before the disk had settled into its current orderly rotation. Methuselah is a population 2 star. It belongs to this ancient cohort. And then there is population 3. These are the very first stars, the ones that form directly from the primordial gas produced in the Big Bang itself. Gas that contained nothing but hydrogen, helium, and a trace of lithium. No carbon, no oxygen, no iron, no heavy elements of any kind. Population 3 stars have never been directly observed. Not one has ever been seen through a telescope. They are theoretical, predicted by our models of cosmic chemistry and star formation, but not yet confirmed by observation. The reason is simple. Population 3 stars are believed to have been massive, possibly extremely massive, perhaps hundreds of times the mass of the Sun. Massive stars burn through their fuel quickly. A star with 200 solar masses might live for only 2 or 3 million years, before exhausting its hydrogen and exploding as a supernova. Population 3 stars would have ignited within the first few 100 million years after the Big Bang and died shortly after. They are long gone. Every single one burned out billions of years ago. But their deaths were not the end of their influence. When population 3 stars exploded, they scattered their internal contents into the surrounding gas. Inside their cores, nuclear fusion had forged the first heavy elements the universe had ever seen. Carbon, oxygen, magnesium, silicon, iron, all created from hydrogen and helium through the searing heat and crushing pressure of stellar interiors. Those elements, blasted outward in supernova explosions, mixed with the surrounding pristine gas and enriched it. The next generation of stars, population 2, formed from this slightly contaminated material. They inherited the chemical fingerprints of the first generation's death. Methuselah is one of those inheritors. Its atmosphere carries traces of heavy elements. Not much, but enough to tell us something extraordinary. The iron, the oxygen, the magnesium in Methuselah's gas were not produced by the star itself. They were already present in the cloud of gas from which Methuselah formed, more than 12 billion years ago. Those elements were placed there by earlier stars, stars that lived and died before Methuselah was born. Population 3 stars, the first generation, the ones we have never seen. In this sense, Methuselah is a fossil record. Its chemical composition is a snapshot of the state of the universe's chemistry at the time and place of its birth. By reading the abundances of different elements in Methuselah's atmosphere, astronomers can reconstruct what the first supernovae must have been like, what masses the first stars had, what kinds of nuclear reactions dominated their interiors, and how efficiently they mix their products into the surrounding gas. Methuselah is a chemical time capsule carrying information about an era we cannot observe directly. And the information it carries is revealing. Methuselah's abundance pattern shows an enhancement of alpha elements, oxygen, magnesium, silicon, calcium, and titanium relative to iron. This pattern is a signature of core collapse supernovae, the explosive deaths of massive stars. Massive stars produce large quantities of alpha elements through nuclear fusion sequences that build up heavier nuclei by adding helium nuclei, also called alpha particles, to lighter ones. When these massive stars explode, they eject those alpha elements into space. Iron, by contrast, is produced in large quantities primarily by a different type of explosion, called a Type 1a supernova, which involves the detonation of a white dwarf in a binary system. Type 1a supernovae take longer to occur because they require a white dwarf to accumulate material from a companion star over millions or even billions of years before reaching the conditions necessary for detonation. In the very early universe, there hadn't been enough time for Type 1a supernovae to contribute significantly. The first stellar explosions were almost exclusively core collapse events from massive, short-lived stars. So the gas from which early population 2 stars formed was enriched primarily in alpha elements, with relatively little iron. This is exactly what we see in Methuselah. Its high alpha to iron ratio is consistent with formation from gas that was enriched by core collapse supernovae alone, with minimal contribution from Type 1a events. This tells us that Methuselah formed early, before the slower iron-producing channel had time to operate at scale. The chemistry is consistent with the age, but Methuselah is not unique. Over the past few decades, astronomers have identified a growing population of extremely ancient, metal-poor stars scattered through the Milky Way's halo. Each one is a window into the early universe, and collectively they're building a remarkably detailed picture of what the cosmos looked like in its first billion years. Some of these stars are even more metal-poor than Methuselah. A star designated HE 0107 5240, discovered in 2002, has an iron content roughly 1/200,000th that of the Sun. That is 1,000 times less iron than Methuselah. Stars this metal poor are extraordinarily rare. Finding one requires sifting through millions of stellar spectra, searching for the telltale weakness of metal absorption lines. But each discovery pushes our chemical record further back in time, closer to the epoch of population 3. One of the most remarkable discoveries came in 2014, when a team of Australian astronomers identified a star in the southern sky, catalogued under a long designation that astronomers typically shorten to SM0313. This star had essentially no detectable iron at all. Its iron abundance was so low that it fell below the detection threshold of even the most sensitive spectrographs. It did, however, contain measurable amounts of carbon. This was a bombshell. Theoretical models had long predicted that the very first low-mass stars to form after population 3 might have been enriched primarily in carbon rather than iron, because certain types of early supernovae could eject carbon-rich material while locking iron away in a collapsing remnant. Finding a star with carbon but no detectable iron was precisely the signature theorists had predicted. It suggested that this star formed from gas polluted by a single population 3 supernova. making it one of the most direct chemical links to the first generation of stars ever discovered. Stars like these, along with Methuselah, form a growing archive. Each one preserves a sample of the gas from which it was born, locked in its outer layers for billions of years, essentially unchanged. Reading their chemical compositions is like reading letters from the deep past, messages written in the language of elemental abundances, telling us what the universe was doing when it was less than 1 billion years old. Methuselah is a lone traveler, a single ancient star drifting through the galaxy on its own. But it is not the only category of ancient survivor. The Milky Way also contains globular clusters, dense swarms of hundreds of thousands of stars that formed together in the early universe and have remained gravitationally bound ever since. These clusters are entire populations of ancient stars, traveling together as a group, and their ages provide an independent check on the timeline that Methuselah's individual age suggests. Their independently measured ages land in the same range as Methuselah's, roughly 12 to 13 billion years for the most metal-poor examples, reinforcing the conclusion that these objects all date from the first billion years of cosmic history. But what makes clusters compelling beyond their role as age benchmarks is what they represent as physical objects. Each one is a self-contained stellar community that has survived intact since the early universe. They have endured every merger, every tidal disruption, every gravitational upheaval that the growing Milky Way has thrown at them across nearly 14 billion years of galactic assembly. Methuselah is a solitary wanderer, one ancient star drifting alone through the galaxy on its eccentric halo orbit. But globular clusters show that ancient stars sometimes survive in crowds. Hundreds of thousands of stars, roughly as old as Methuselah, bound together by their own gravity, traveling as a single system through the galaxy for almost the entire history of the universe. One cluster in particular illustrates how deep this antiquity runs. Omega Centauri, visible to the naked eye from the southern hemisphere as a hazy smudge in the night sky, is the Milky Way's most massive globular cluster. It contains roughly 10 million stars and spans about 150 light-years across. But Omega Centauri may not be a true globular cluster at all. Its stars show a spread in chemical compositions and ages that no single burst of star formation can explain. Many astronomers now believe Omega Centauri is the stripped core of a dwarf galaxy that the Milky Way swallowed billions of years ago. The galaxy itself was torn apart by tidal forces, its outer stars scattered into the halo, but its dense nucleus survived intact, orbiting within the Milky Way ever since as what we now classify as a cluster. If this is correct, then Omega Centauri is not just old, it is a fossil of a galaxy that no longer exists. A gravitationally bound remnant of a system that predates the Milky Way's current structure. There is something visceral about globular clusters that a single star doesn't quite convey. When you look at M13 through a good telescope on a dark night, you see hundreds of thousands of stars packed into a glowing sphere. Nearly every one of those stars is older than 10 billion years. Many are likely as old as Methuselah or older. You are looking at a city of ancient suns, each one burning since before the Milky Way had a disk, since before most of the stars you see in the night sky existed. These clusters are not just old objects. They are old communities, gravitationally bound assemblies that have traveled together through the galaxy for almost the entire history of the universe. And what they tell us is that the universe wasted no time. Star formation began early and proceeded quickly. The first stars ignited within the first few 100 million years after the Big Bang, and they died and enriched their surroundings within a few million years after that. The second generation, population 2, began forming almost immediately from the enriched debris. Methuselah's existence at roughly 12.7 billion years old means that by the time the universe was about 1 billion years old, at least some regions had already cycled through an entire generation of stars, enriched their gas, and begun forming new stars from that enriched material. The cosmic assembly line was running from the very beginning. This rapid onset of star formation connects to another major chapter in cosmic history, the epoch of reionization. For the first few 100 million years after the Big Bang, the universe was filled with neutral hydrogen gas. This gas was opaque to ultraviolet light. The universe was dark. Then the first stars ignited, and their intense ultraviolet radiation began ionizing the surrounding hydrogen, stripping electrons from atoms and creating bubbles of transparent, ionized gas. As more stars formed, these bubbles grew and merged. Eventually, the entire universe was reionized, transitioning from opaque to transparent. This process, the epoch of reionization, is thought to have occurred roughly between 400 million and 1 billion years after the Big Bang. Methuselah was born during or shortly after this epoch. The star that exists today, still quietly burning in our neighborhood, formed during the era when the universe was transitioning from darkness to light. The first generation of stars was flooding the cosmos with ultraviolet radiation, ionizing hydrogen, and sculpting the intergalactic medium into the structure we see today. Methuselah's birth was part of that story. Its formation was enabled by the enrichment from the same early stellar populations that were driving reionization. Every time you look at Methuselah through binoculars, you are looking at an object that was present for one of the most transformative events in cosmic history. It's worth pausing here to picture what the universe actually looked like when Methuselah was born, because it was nothing like the cosmos we inhabit today. 1 billion years after the Big Bang, the cosmic microwave background radiation was still warm, roughly 20 Kelvin, about 7 times hotter than it is now. Space itself still glowed faintly in the far infrared across its entire volume. The universe was smaller, denser, and younger in every sense. The elegant, large-scale structure we observe today, the cosmic web of galaxy filaments separated by enormous voids, was only beginning to take shape. Dark matter had been pulling itself into clumps and sheets since the first few 100 million years, forming a gravitational scaffold, but the visible structures threaded along that scaffold were still primitive. There were no grand spiral galaxies. Nothing resembling the Milky Way existed anywhere. Instead, the universe was populated by small, irregular proto-galactic fragments, clumps of gas and dark matter containing perhaps a few million to a few 100 million solar masses of material. These fragments were dense, turbulent, and chemically primitive. Some had already formed their first stars, others were still collapsing, not yet dense enough to ignite nuclear fusion. The gas available for star formation was almost entirely hydrogen and helium. Heavy elements existed only in tiny pockets where the first generation of massive stars had already lived and died, seeding their immediate surroundings with carbon, oxygen, and traces of heavier nuclei. But these enriched regions were small and localized. Most of the gas in the universe was still pristine, untouched by stellar processing. Cooling was the challenge. In the modern universe, gas clouds collapse into stars partly because heavy elements help the gas radiate away heat efficiently. Carbon and oxygen atoms are particularly effective coolants, emitting photons at specific wavelengths that carry energy away from the cloud, allowing it to contract further. But in the early universe, with almost no heavy elements available, this cooling channel was largely shut off. Gas had to cool through other mechanisms, primarily through molecular hydrogen, which is a far less efficient coolant. This meant that the first star-forming clouds tended to be hotter and more massive than their modern counterparts, which is one reason theorists believe population 3 stars were so large. Methuselah formed in one of the rare pockets where enrichment had already occurred. Some nearby population 3 star or stars had already exploded, injecting just enough heavy elements into the surrounding gas to shift the cooling physics. With even a tiny admixture of carbon and oxygen, the gas could cool more efficiently, fragment into smaller clumps, and form lower mass stars. Stars like Methuselah. This is why Methuselah's low mass is itself informative. A star of 0.75 solar masses could not have formed easily from truly primordial gas. The presence of trace heavy elements in its atmosphere tells us that the gas had been pre-processed, that at least one cycle of stellar birth and death had already occurred in its immediate vicinity, and that the products of that cycle had mixed into the local gas just enough to change the physics of collapse. The proto-galactic fragment in which Methuselah was born may have contained only a few tens of millions of solar masses of material. It would have looked nothing like a galaxy to our eyes. No disk, no spiral arms, no central bulge. Just a lumpy, irregular knot of gas and young stars embedded in a halo of dark matter. One small piece in the larger puzzle that would eventually assemble into the Milky Way. Over the next several billion years, dozens or hundreds of fragments like this one would merge, collide, and accumulate, gradually building the galaxy we see today. Methuselah would survive all of that, riding its elongated orbit through each successive merger, each rearrangement of the growing galaxy's gravitational landscape. The James Webb Space Telescope, launched in late 2021, is now observing galaxies at precisely this epoch. Webb's infrared instruments can peer back to within a few 100 million years of the Big Bang, capturing light from the first galaxies as they were assembling. Early Webb results have revealed that galaxies formed earlier and grew more quickly than many models predicted. Some of the galaxies detected at very high redshifts are surprisingly bright, suggesting vigorous star formation was underway even earlier than expected. These observations are painting a picture of a universe that was remarkably active in its youth, rapidly forming stars, building galaxies, and enriching its gas with heavy elements. Methuselah complements these observations in a unique way. Webb sees the early universe from afar, capturing light that has traveled for more than 13 billion years. The galaxies it observes are unresolved smudges, too distant to study in detail. You can measure their total brightness, their rough colors, their overall chemical properties, but you can't study individual stars within them. Methuselah, by contrast, is right here. It's 190 light-years away. You can take a detailed spectrum. You can measure dozens of individual element abundances. You can determine its mass, its temperature, its evolutionary state, its velocity through the galaxy. You can study it with a level of detail that will never be possible for any star in a galaxy 13 billion light years away. This makes Methuselah and stars like it a bridge between two different ways of studying the early universe. Distant observations through Webb show you what the early universe looked like in broad strokes. Nearby ancient stars show you what the early universe's chemistry was, element by element, line by line, with precision no distant observation can match. Together, they tell a more complete story than either could alone. There is also something philosophically striking about Methuselah's continued existence. Stars are not eternal. They are born, they burn, and they die. The more massive a star, the shorter its life. The most massive stars, dozens of times the mass of the Sun, burn through their fuel in just a few million years. Our Sun, a modest star by cosmic standards, will last about 10 billion years. But very low-mass stars, red dwarfs, with a fraction of the Sun's mass, burn so slowly and so efficiently that they can last for trillions of years, far longer than the current age of the universe. Methuselah is not a red dwarf, it's more massive than that. But it's also not particularly massive. Its mass is estimated at roughly 0.75 to 0.8 solar masses, about 3/4 the mass of the Sun. Stars of this mass burn slowly enough to last well over 12 billion years, but they don't last forever. Methuselah is now entering the subgiant phase, beginning the transition that will eventually turn it into a red giant. It has used up most of the hydrogen in its core. It is in the late stages of its life, not the end, but the beginning of the end. This means we are seeing Methuselah at a particular moment in its biography. A few billion years from now, it will swell into a red giant, shed its outer layers, and leave behind a small, dense white dwarf that will cool slowly over trillions of years. The star that has survived since the cosmic dawn will eventually die, but for now, it burns. It has been burning since before the Milky Way's disk existed. It has been burning since before the Sun was born, since before the Earth existed, since before the solar system's parent cloud of gas had even begun to assemble. Every planet in our solar system, every mountain and ocean on Earth, every living thing that has ever existed, all of it is younger than this one faint star in Libra. Think about the journey Methuselah has taken. It formed in the halo of the young Milky Way, or perhaps in a smaller galaxy that was later absorbed by the Milky Way. In the early universe, galaxies grew through mergers. Small proto-galactic fragments collided and combined, gradually building up larger structures. The Milky Way, as we know it today, with its elegant spiral arms and thin rotating disk, didn't exist yet. It was a chaotic assembly of gas clouds and small stellar systems pulling together under gravity. Methuselah formed in that chaos, and ever since it has been orbiting the growing galaxy on its long, looping halo orbit, passing through the disk periodically, witnessing the Milky Way take shape around it. It was already billions of years old when the thin disk of the Milky Way began to form. It was already ancient when the Sun ignited 4.5 billion years ago. It was circling the galaxy when the first single-celled organisms appeared on Earth. It was circling the galaxy when multicellular life evolved, when dinosaurs walked the planet, when the asteroids struck and wiped them out, when mammals diversified, when primates appeared, when humans evolved, when we built telescopes and pointed them at the sky, and finally measured the age of this star that had been watching over us the whole time. Not watching, of course. A star has no consciousness, but the metaphor captures something true about the relationship between observer and observed. We are temporary beings studying an object that has persisted for almost the entire history of the universe. Methuselah's orbit through the galaxy is itself a piece of evidence, and reading that evidence is part of a growing scientific discipline called galactic archaeology. The idea is that stars carry more than chemical information. They also carry kinematic information, a record of their motion through the galaxy encoded in their velocity, their orbital shape, and their trajectory. By measuring these properties for large numbers of ancient stars, astronomers can reconstruct the history of how the Milky Way was assembled. We already know Methuselah's orbit is fast and eccentric, nothing like the orderly circular paths of disk stars. But galactic archaeology reads that orbit as more than just a sign of age. It reads it as a clue to origin. The specific shape of the orbit, its inclination relative to the galactic plane, its eccentricity, how deeply it plunges toward the center, and how far it swings into the halo, all of this encodes where the star was when the Milky Way's gravitational field captured it into its current trajectory. That birthplace may not have been the proto-Milky Way at all. It may have been a separate, smaller galaxy entirely. This second possibility is increasingly favored by modern research. Over the past decade, large-scale surveys using data from the Gaia satellite have revealed that a significant fraction of the Milky Way's halo stars, including many of the most ancient and metal-poor ones, share orbital properties that trace back to a single massive merger event. Roughly 8 to 10 billion years ago, the Milky Way collided with and absorbed a smaller galaxy, now called Gaia Enceladus. This was not a gentle process. The incoming galaxy was shredded by tidal forces. Its stars scattered across the Milky Way's halo on elongated, eccentric orbits. Today, the debris of Gaia Enceladus makes up a large portion of the inner halo. Stars that once belonged to a separate galaxy now orbit within our own, carrying the chemical and kinematic signatures of their foreign origin. Whether Methuselah is a Gaia Enceladus star or was born in the proto-Milky Way itself is still debated. Its orbit and chemistry are consistent with either origin, but regardless of which proto-galactic fragment it formed in, the broader picture is the same. The Milky Way was not born as the stately spiral we see today. It was built through mergers, through the gravitational capture and absorption of dozens of smaller systems over billions of years. Each merger added stars to the growing galaxy, stirring them into the halo, mixing populations from different origins into a single orbiting swarm. Methuselah is one member of that swarm. Its orbit carries the memory of whatever system it was born in, a gravitational fossil as informative as the chemical fossil preserved in its atmosphere. Other ancient halo stars tell similar stories. Some share orbital properties that link them to the Sagittarius dwarf galaxy, a smaller system that the Milky Way is still in the process of absorbing today. Others belong to kinematic groups associated with even older, more completely disrupted mergers, whose parent galaxies have been so thoroughly shredded that only the shared orbits of their former stars reveal they ever existed. By mapping these orbital families and cross-referencing them with chemical abundances, astronomers are piecing together a detailed merger history of the Milky Way, identifying which stars came from which progenitor galaxies and when those mergers occurred. Methuselah sits at the intersection of all these threads. Its age tells us when it formed. Its chemistry tells us what the gas looked like when and where it formed. Its orbit tells us where that formation happened relative to the Milky Way's assembly. Together, these three lines of evidence turn a single faint star into a probe of the early universe's structure, the first cycles of chemical enrichment, and the gravitational mergers that built our home galaxy. A single star, observed through binoculars from a backyard, carrying in its light the story of cosmic dawn, the death of the first stars, and the assembly of the Milky Way. That is galactic archaeology at its most elegant. There is a final question worth considering. Could there be stars even older than Methuselah? In principle, yes. If population 2 stars began forming within the first billion years after the Big Bang, some might have formed even earlier, within the first 500 million years. A star with 0.6 or 0.7 solar masses, slightly less massive than Methuselah, would burn even more slowly, and could still be on the main sequence today after 13 billion years, barely showing its age. Such a star would be extraordinarily metal poor, perhaps with iron abundances thousands of times below the Sun's, and it would likely be faint, difficult to find among the billions of brighter, younger stars in the galaxy. The search for such stars is ongoing. Large-scale spectroscopic surveys are sifting through millions of stellar spectra, flagging candidates with unusually low metal content for follow-up observation. Each new discovery pushes the known record further back. Each one adds another data point to our understanding of the first billion years. It is possible, even likely, that there are stars in the Milky Way's halo right now that are older than Methuselah. Stars that formed within a few hundred million years of the Big Bang, carrying the chemical signatures of the very first supernovae. We just haven't found them yet. Or we've observed them, but haven't yet measured their ages precisely enough to recognize how old they truly are. They might be sitting in existing catalogs, waiting to be identified by a future survey or a future student who looks at the spectrum and notices something extraordinary. But even without finding anything older, Methuselah itself is a profound object. It represents something we rarely encounter in science, a piece of physical evidence from the very beginning. Most of what we know about the early universe comes from radiation, photons that have been traveling since the cosmic microwave background was released, or light from distant galaxies seen as they were billions of years ago. These are images, snapshots, recordings of the past. But Methuselah is not a recording. It is the thing itself, a physical object that was there, that formed from the gas of the infant cosmos, that has been present for the entire subsequent history of the universe, and that is still here now, still burning, still accessible, still available for study. It is as if you found a piece of the original clay from which the first pot was ever made, still intact, still holding its shape after all these millennia. You could study it. You could analyze its composition. You could learn about the soil and water and conditions of the place where it was made. That's what Methuselah offers us. Not a reconstruction, not a model, not an indirect inference. A real, tangible piece of the ancient universe drifting through our cosmic backyard. And the fact that we can read its story is itself remarkable. 200 years ago, nobody could have determined the chemical composition of a star. The idea would have been dismissed as absurd. In 1835, the French philosopher Auguste Comte specifically cited the chemical composition of stars as an example of knowledge that would forever remain beyond human reach. He could not have been more wrong. Within a few decades of his pronouncement, spectroscopy had revealed the chemical makeup of stars with extraordinary precision. Today, We can measure individual element abundances in a star 190 light years away, compare them against models of supernova nucleosynthesis, infer the mass and explosion energy of a star that died more than 12 billion years ago, and place the result in the context of a cosmological timeline calibrated by microwave radiation from the birth of the universe. That chain of reasoning, from photons arriving at a telescope tonight to the conditions in a gas cloud 1 billion years after the Big Bang, spans almost the entire age of the cosmos. It connects the present moment to the earliest epoch of star formation through an unbroken thread of physics, chemistry, and meticulous observation. It is one of the most astonishing intellectual achievements our species has produced. Methuselah will keep burning for a while yet. A few more billion years, perhaps, before it exhausts the last of its reserves and begins its final transformation. When it finally dies, it will leave behind a white dwarf, a small dense ember that will cool over trillions of years, long after the sun has died, long after Earth is gone, long after the Milky Way itself has merged with Andromeda and settled into a vast elliptical galaxy. That white dwarf will carry, locked in its crystallizing interior, the last traces of gas forged in the first supernovae of the universe. But tonight, Methuselah is alive. It is burning hydrogen into helium, slowly and steadily, as it has been doing since before our galaxy had a disk, since before the sun existed, since before the Earth was even a possibility. If you go outside tonight and look toward Libra, and if the sky is dark enough and you have a pair of binoculars, you can see it. A faint point of light among thousands of others. It doesn't look special. It doesn't announce itself. It doesn't call attention to the fact that it has been burning since the universe was young. But it has. And the light entering your binoculars tonight, those photons that have been traveling for 190 years since they left the star's surface, were emitted by an object that remembers the cosmic dawn. Not in any conscious way, but in the only way a star can remember. Through its chemistry, through the atoms in its atmosphere, through the elemental fingerprints left by the very first generation of stars that ever lived and died. You are looking at a survivor, a relic, a time capsule from the first chapter of cosmic history, and the fact that it once appeared to be older than the universe itself, that paradox that drove a decade of meticulous scientific investigation, turned out to be not a flaw in our understanding, but a tribute to the difficulty and beauty of the work. The universe was never broken. Our measurements just needed to catch up. And when they did, they revealed something better than a paradox. They revealed a star that formed when the universe was barely beginning, that has been burning ever since, and that will keep burning long after everyone alive today is gone. Methuselah is not older than the universe, but it is almost as old as the universe. And somehow, that is even more extraordinary.